or put another way, I want and B here as, well, for me, B is probably going to be upper triangular instead of lower triangular. So no? Should lower triangular?
Whatever you prefer.
I did see one clever author who had two opposed Borels in their paper. One was B and the other was B+. I thought that was pretty good. So anyway, this might be, and I want X to live inside G mod P and D to be B equivariant. And so the example is, in the Grassmannian, is I've got the, I take, let's see. So I'm going to identify the Grassmannian with column spans of n by k matrices of rank k, n by k matrices. I guess it's equal to that, to be honest. So if you want to tell somebody a k-plane in the a k-plane in n space, you can pick a basis for it of column vectors and then tell them what your columns were. Now, what the B action is doing on here, and here it's doing column operations.
You don't want rows times of k by n matrices.
Well, maybe. So the question is whether I want to deal with G mod P or P dom G. Right? So since I could put these guys over on the other side, and then I'd be dealing with row spans. Let me stick with this for just a moment.
So we should view B as acting by matrix multiplication.
B is acting by matrix multiplication. Yep. So here it's just attacking on the left by as it inside G. Here it's the way column operations is about left multiplication. And so that means that you can rewrite this. If you think about the B orbits, you can, before I think about the B orbits, I think just about column spans. I could think about column spans. Well, actually, there's another equality. I could think about column spans of reduced row echelon form, n by k matrices, rank k again. So what those look like is I've got a 1 in each column, and I've got 0 below, and there's various other stuff I've been there's various other stuff I've been able to kill using column operations, and then there's all this stuff that I haven't. So that's what a general reduced row echelon form matrix looks like. And since I only care about the column span, it's okay if I first put my matrix into reduced row echelon form. The nice thing about doing that is that now every k-plane is the column span of a unique matrix in this form. Then what are the B orbits doing? They're doing upward row operation. Did I? So I see. The B at this point was doing the row operations. Yep. What you can do with the row operations is kill off those dots just above. So if I want a B, if I think about the B orbits on the Grassmannian, there's one of them for every placement of the ones. There's n choose k many places that I could have my pivot columns arranged, and each one of those is giving me one B orbit on the Grasslanian. So these are the Brujas cells. So I'll have X will be the B orbit through some, in this general setup, some D orbit through some permutation matrix, P. So let me call that guy X super pi. A Schubert variety. And now I'm going to give you a recipe for computing equivariant cohomology classes of these Schubert varieties. So it's based on the Botz-Samuelson crack that we're going to turn many times. What you do is, so the input to this is I have some guy X mapping, maybe not including, just mapping B equivariantly into G mod P. And I have a simple root, alpha, and I have the minimal parabolic corresponding to that simple root. So what this sort of thing looks like is it's not quite the upper triangular matrices, it's a little bit more. Okay? So here I might have it in the I plus 1 and I row and column. I was thinking about the ith simple root for GLN. Then more generally for other groups, you don't talk about I going from 1 up to n minus 1, you talk about a simple root if you want to index one of these minimal parabolics that's just a little bit bigger than Borel. I'm going to take the product of these two and divide by B. So P alpha, because it contains B, it's got a B action on the left and the right. X has a B action on the left because I said so over here. This super B means I want to divide by, so this by definition is I take P alpha, I cross it with X, and I divide by the B action that's here and there. And I claim that this new space, so the input is alpha and X, and the output is this. Okay? It's another space with a well-defined map to G mod P. So, okay, so say it one more time. The input is X that's mapping B equivariantly to G mod P, and alpha simple root. And the output is this space P alpha cross under B X. That again has a map to G mod P. So first, why does this space have a map anymore? So X is not invariant under P alpha. But by the time it ends up in G mod P, we know how to hit it with an element of P alpha. So that's going to be my map from P alpha cross X into G mod P. You map your guy little x and your group element, you map it in, and you apply your group element. Probably write that bigger, huh? So, Gx is mapping to G applied to X in G mod P. Why does it make sense after I've divided by this B action? All that's going to do is it's going to replace this with B inverse and this with B. But when you apply this guy to that guy, you still get the same answer. So it's well defined, this map, after I divided by B. This guy, even though I divide by the right B action, still has the left B action. So that's why it still has a B equivariant map. what you can do with this is I've got this map I from X to G mod P, and I push forward the class 1, and it goes to, maybe X is including, it goes to, I'll call X living inside the B equivariant cohomology of G mod P, or the T equivariant cohomology of G mod P. If B is acting, then T is acting, and so I'm going to be defining this, these T equivariant classes. What about this new space, P alpha cross under B X? So I'm trying to go to G mod P, and I want to know this is going to get me what class on here. So to be clear, this space is a little bit bigger than X itself. So how much bigger is it? Well, this space has a forgetful map projection to the first factor to CP1. So P alpha, remember, was one dimension larger than B. When you take the quotient, you get this one-dimensional space with the torus action. That's just a copy of CP1. So this thing is in fact an X bundle over CP1. It's that associated bundle construction coming up again. I want to take the class 1 on here and push it into there and get some formula for for that image. I'm going to start with the class 1 on here and pull it back to there and get the class 1 and then push it in. Down here, there's a nice formula. So on CP1, let's look at this story that we were doing here in CP1. I've got the class of this point, which, if you restrict to these points, is maybe I'll call this point south and this point north on my CP1. So the class of south, restricted to the 2 points, is this arrow here and 0 at the other end. The class of north, restricted to these 2 points, is this arrow here and 0 at the other end. But what I want is the class 1. And so I'm going to write it as south minus north divided by this arrow. So that division is not fair because we're working in these polynomial rings and we can't divide by this linear factor unless we tensor with the fraction field of H star t. So the calculations I'm going to do here will not let me calculate directly in Quiver cohomology. It'll only let me calculate inside that guy tensored with the fraction field of H star t. But that's good enough. So I have this equation down here, 1, and with the alphas and such, what it's saying is that 1 is equal to the class over the base point, B mod B, minus the class over the other point, divided by minus alpha. Minus alpha being the weight on the extra direction that's in P alpha that isn't in B. I pull this equation back to here, and it gets me the pre-image of this point is X, the pre-image of that point is R alpha applied to X, and then I push it into here. And I get that the class of P alpha applied to X is X minus R alpha of X divided by minus alpha. So this is the equivariant topology that's producing these operations. This thing is called a divided difference operation. So let's do some calculations. calculations with those operations in this diagrammatic picture. And produce all the Schubert classes on flags in C3. So this is this picture, this Bowen polytope for flags in C3, which is a line contained in a plane contained in C3. How am I getting this picture? I think about the t-fixed points when I scale the 3 coordinates in C3. And for these guys to be invariant, they have to be coordinate subspaces. So this coordinate subspace is either using the first or second, third coordinate, and then this is using one more of the coordinates, and then this is using whatever wasn't used so far, and that's 3 factorial choices. And here I have 3 factorial points. Let me label them with what choices I make. 1, 2, 3, 2, 1, 3, 1, 3, 2, 3, 1, 2, 2, 3, 1, 3, 3, 2, 1. So what I've drawn here is not just the convex hull of the entire flag variety. I've also drawn the convex hulls of certain of my favorite subvarieties that I won't talk about yet. But there's these nice 9 CP1s that are invariant under the torus action, and I've drawn them in as well. So this is a 2-dimensional picture. I only have a 2 torus on this, the 2 torus in PGL3. But even though it looks a little bit 3-dimensional, but you can't, well. So I want to end with a couple of these calculations. Let's start with the class of this point. So when I restrict it to other points, I get 0. I restrict it back to that point, and I get the product of the weights on the normal directions, which are all pictured there. So let's compute. Let's compute. I didn't give you notation for this operation yet. It's called the partial with this minus alpha. Then I want to apply this operation to this equivariant cohomology class. So I need to take this guy, flip it with respect to alpha, and then divide by this. So I'm going to take that, flip it over and subtract, and then divide by this. So I just have this and this left over here. When I flip this over, I will get that thing, but then I'm supposed to subtract it off, but then I'm supposed to divide by this, and this is equal to negative that, so I get that. And 0 is still here.
So on the left-hand picture, in the top left corner, is that just a 0, or is
Yes.
that some other marking?
That's a 0. Yep, 0 at all the points that aren't at my point, or restricted class, and he safely misses them. All right, let's, so I got there by doing this operation. Let's do that one. So I'll take this and flip it like that. So these 2 points are going to come down there and subtract off and divide, and I end up with this. So and then I could do, maybe I'll do the original one more time. And I think you're going to get 1 everywhere. So geometrically, what was I doing? I started with a point inside G mod P, and I applied these operations. Each time, I made my object 1 dimension bigger, right? I've got this X bundle over P1, so it's 1 dimension bigger than X. and then I pushed it into Gmod P, and ended up with something one dimension bigger than what I had. So the space of all flags is 3-dimensional, because it's GLN mod B, GL3 is 9-dimensional, upper triangular is 6-dimensional. So this is a three manifold. I'm starting with a point. I'm sweeping it around with my first moment parabolic, and it becomes this P1, the P1 who's got that moment polytope. Then I sweep it around this parabolic, and it becomes the surface that has this moment polytope. And then I sweep it around using this parabolic again, and it becomes the entire threefold. So it's just giving me class 1 of ring homology, which restricts to 1 everywhere. So the two things we're going to head to first off next time are doing more calculations like this, but on the Grassmannian and not too directly. That's what the puzzle pieces will be for. And souping up these divided difference operators to produce more interesting classes. One thing I forgot I didn't mention about these is they square to 0, and we'll find ones next that square to 1. To actually get you an action of SM. So let me lie first. If I have a map of smooth compact manifolds, then there's a push forward operation in control homology. So you Poincare dualize to homology, map in homology, and Poincare dualize again, and you map from cohomology to cohomology. So now I don't really want to do that in equivariant cohomology because it looks like I would have to go through those infinite dimensional spaces to do it. So nonetheless, there is a way of doing push forwards in cohomology, in equivariant cohomology. You have to first understand how to do it for inclusions, then you have to understand how to do it for fibrations, then you use the graph construction to say every function is an inclusion followed by a fibration. So this is how they do it in Etiabot and with map and equivariant cohomology through that stupid trick. The main thing you know about this push forward map in cohomology is that it's not a ring homomorphism, because it's based on homology is one way to say that. Instead, it's only a module homomorphism over the only thing that would make sense, which is the cohomology of the target.
And it's supposed to send like 1 to some sort of geometric classes or something like that.
Right, so in particular, if you believed the Poincare duality thing, then I'd say I start with 1, the Poincare dualized, that's now the fundamental class of X. And that gets me its class inside the target, which I then want to turn into a cohomology class. Yeah.
Can you say why it's called moment polytope?
So there is a map actually from the entire M, and this is a statement that's only true when we're dealing with complex manifolds and not more general algebraic geometry stuff. But in this complex situation that's good enough for me, there's an actual function from M to the polytope, not just from the fixed points to the polytope, but from the entire M. So for example, with CP2, the map is X, Y, Z maps to the norm of X squared, comma, which way do I really want to do this? Norm of Y squared, comma, norm of Y squared plus Z squared, I think is how I did end up with this. Okay, sorry. I chose these in a way to confuse myself. But something like this. Norm of X squared, norm of Y squared, norm of Z squared. So take that vector in R3. Now it's not well defined because I can scale these and these would change. So divide by all that. And now where is this going? It's going to vectors in R3, non-negative, such that the sum of the three coordinates is 1, and that's exactly to the standard triangle connecting the three basis vectors in R3. So that is in particular taking the 3T fixed points to the vertices. So one thing I like about this definition is that it doesn't actually require C here. I could have projective space over a finite field and a subvariety of that, as long and torus acting on things, and I can still talk about this polytope. And that's good enough for me to draw pictures with. I don't really need the entire roller graph to find out the whole thing.
More questions?
On the fixed point, the tangent space of the fixed point is at the T action. Is that related to these arrows that you can?
Yes, so so let's say I've got a point and it's got this tangent space, and so I know if I'm doing things over C that the manifold is going to be locally T equivariantly diffeomorphic to the tangent space. So I could use a metric, an exponential map, and so on. So to get me this local diffeomorphism. So that means, in particular, if I have a weight vector in the tangent space, I could say let's consider the codimension 1 subtorus that fixes that weight vector. So in that way, I can pick out of my manifold nice subvarieties from the fixed point sets of these codimension subtorus. I can pick out these interesting submanifolds of my original manifold that will be torus invariant and look at their mode polytopes. So what's happening, for example, here is I have this point in my three-dimensional complex manifold, and I know that going through that point will be 3 CP1s in the actual manifold. And the mode polytopes of CP1s will be this guy, and that guy, and that guy. So I can always see the weights on my tangent space actually at my points, as long as I draw not just the mode polytope for the points, but also for all of the CP1s. Then I will see all the weights. It might be hard to see whether the weight is this versus that versus that. So lengths is extra data beyond just exactly the polytope with the lines in it itself. But at least you have the weights up to multiple just from looking at the picture.
Okay, let's thank Ellen again. Now we have a discussion for about 15 minutes, so if you want to hear what I mentioned before, discussion.